So in addition to the physical properties of the ocean in terms of the vertical stratification of seawater, the other factor that has a big impact on the distributions of various chemicals throughout the ocean is the circulation. So how waters are moving around. That circulation is determined primarily by wind forcing of wind, but also buoyancy forcing of ocean circulation. And so if we've got the Earth here and the sun is way out, quite far away in space, such that the incoming radiation is essentially along parallel rays of light that are coming in. And if the sun has a solar constant at the Earth's orbit of S0, we define it as 1,370 watts per meter squared. That's the amount of energy that's coming in and that's available to hit the Earth. What happens, though, is because of the shape of the Earth and the fact that the Earth is a sphere, at the high latitudes, this incoming energy is spread out over a larger surface area than it is when it's coming in at the low latitudes near the equator. So the result of this is we've got essentially less heating per unit of land area, land or ocean area, and at the equator we've got more heating. And so with the same incoming radiation, it's just a matter of how it's spread out. That's why in the winter here in Fairbanks, the sun is at such a low angle that not much of that is actually being absorbed by the landscape. And that's why it gets so cold here. And so the issue with this is that this differential heating causes an imbalance in the planetary system, in the planetary heat system. And so this heat must be must be redistributed and transported to the poles, because it's a law of thermodynamics that heat moves from areas of high temperature to areas of low temperature. And so this heat is going to be transported towards the poles. It turns out about 2/3 of this heat transport is done by the atmosphere, and about 1/3 of this transport towards the poles is done by the oceans. So if this was just a still planet and it wasn't moving, and we were getting this incoming radiation as we are, we would have essentially less heating here, more heating here. The planet is radiating heat from all portions of its surface back into space and losing heat back into space that way. And so what that generates, this differential here generates cooling and sinking air in the atmosphere, and essentially heating, expansion, and rising air that occurs near the equators. And in the absence of any rotation, that would lead to a circulation that looks something like this, where we've got rising air at the equator, and that air moving down and sinking at the poles, and then moving back towards the tropics. But it turns out that, of course, we know that Earth is rotating, and it's moving towards the east, and the surface is moving towards the east throughout the day. And as a result, we've got fast motion at the equator, and we've got very slow motion of rotation up at the high latitudes. And this rotational effect creates what's known as the Coriolis effect. And essentially what the Coriolis effect means is that moving objects are deflected by this rotation. And so they're deflected to the right in the northern hemisphere, and to the left in the southern hemisphere. And so that's because as a moving object maybe starts out here at the equator, and let's suppose it's moving in this direction. Well, it has a component of motion initially due to the fast rotation of the Earth. And as it moves up towards the pole, it's actually that rotational motion is slowing down. And so what happens is it has to conserve angular momentum. And as a result, it speeds up in the direction of the rotation. And so in order to maintain that angular momentum. And so in the northern hemisphere, these objects are deflected to the right, and similarly, or in the opposite manner, in the southern hemisphere, objects or moving fluids such as the ocean or atmosphere are deflected towards the left.